everyone, my name is Liang. I'm currently involved at Lamar University in America for my doctoral degree in major with electrical engineering. This is a presentation about the paper, Effects of Link Disruption on LTP for Mass Communications. I am very happy and thankful to be able to attend this 2021 YSAS conference. Before the presentation, I would like to thank the efforts of all the authors in our team, and especially the support of my academic professional advisor, Dr. Wang. Right now, I will give my speech on this presentation. This is the outline of the presentation. In this presentation, as you can see, it made up a total of 6 parts. First of all, let's talk about the background. Delay or disruption-tolerant networking has been recognized as the only candidate networking technology that approaches the level of maturity required to provide a reliable data delivery service in regards to interplanetary internet. Developed as the main data transport protocols of DTN to operate over unreliable space communication channels, LTP, the Licklider transmission protocol is developed to provide reliable and highly efficient data delivery over unreliable communication channels. Now I will explain about the concept of link disruption. Link disruption events in interplanetary internet are generally caused by a lack of limited relay transit capability between the source node on the planet and the destination node on the Earth. They can occur over both the direct planet-Earth link and the broadly adopted indirect relay-based data links. As a result, the data links connecting the source node on the Mars surface and the destination node at Earth's ground station are frequently disrupted. This leads to frequent interruptions to the communication channels, making them unavailable for the end-to-end data delivery. So we could get the consequences that transmission performance and efficiency of data delivery are severely degraded, especially in mass communication having an extremely long link propagation delay. In this paper, analytical models are built in estimating the RTT and data block delivery time of LTP in cislunar communication. The models focus on the essential time components involved in reliable data delivery of LTP in presence of link disruption. Although the models are built for LTP in moon communication, they are applicable also in mass communications. So this is the formula about RTT of the analytical modeling. It is a system model for the operation of LTP in mass communications. The RTT for reliable data delivery in presence of link disruption can be estimated as double the one-way light time between the Mars and the Earth, plus the transmission time for an encapsulated LTP data block at the link layer, and then plus the transmission time of an RS, which is only be triggered by a successfully delivered CP segment. Finally, still need to plus the total time effect to data block delivery caused by the link disruption event. We have experimental infrastructure and set up the configurations for experiments. A PC-based space communications and networking testbed was adopted as the experimental infrastructures for the data block delivery experiments. To achieve reliable transmission service of LTP, the entire LTP block is set as 100% read data. The one-way link delay of 10 minutes was introduced to each of the data and acknowledgement channels, where each bundle size is 5 kibytes long. LTP data block is configured to have 40 bundles aggregated within a block, that is 40 bundles per block. The effect of the channel rate asymmetry on file transmission was also implemented by configuring a downlink channel rate of 250 kibytes per second and an uplink channel rate of 25 kibytes per second, leading to a channel ratio of 1/10. There are sightings of link disruption events for two sets of experiments in case 1. From this table of experimental setup and configurations, you could see that we actually take two contrast experiments in case 1 totally. The table lists the sighting and parameters of link disruption events, meaning the link starting time and various link disruption durations for two sets of experiments named as Experiment 1 and Experiment 2, conducted in case 1. Experiment 1 and Experiment 2 are different with respect to their link disruption starting time, 7 minutes and 13 minutes from the beginning of the transmission, respectively. However, for each set of the experiments, various link durations are configured for the single link break event, including 5 minutes, 10 minutes, 15 minutes, 20 minutes, 30 minutes, 45 minutes, and 60 minutes. Figure 1 presents a comparison of two sets of experiments in case 1 over a clean deep space channel with respect to various durations of a link disruption. It is observed that for both Experiment 1 and 2, the extra number of transmission attempts caused by the link disruption increase along with an increase in the duration of link disruption. This is reasonable. A longer link disruption leads to a long waiting time at the sender, which results in an increase of the number of the checkpoint timer aspirations at the sender, and thus an increase of the extra transmission attempts. Figure 2 presents a comparison of the corresponding RTT between Experiment 1 and Experiment 2. Obviously, similar to the variation of the actual number of transmission attempts in Figure 1, the RTT shows a similar increasing pattern with the increase in the duration of link disruption. This is reasonable because the duration of the link disruption event experienced during block delivery is also counted as a part of RTT. Figure 3 presents a comparison of corresponding good put performance between two sets of the experiments. Good put is defined as a ratio of the data block size and the block delivery time. The increase of the RTT in Figure 2 surely leads to a longer block delivery time for each run. As the block size is the same for all the runs, the good put consistently shows degradation with an increase in the duration of the link disruption. The experiments in case 2 are configured to run with two link disruption events that start at different times. Figure 4 and Figure 5 present a comparison of the extra number of transmission attempts caused by the link disruption and the RTT with respect to the time interval between two link disruption events for successful block delivery, respectively, between experiment 1 and experiment 2. The significant difference in the extra transmission attempts between experiment 1 and experiment 2 is on their variation trend, along with an increase in the duration of link disruption. Their significant difference is related to the starting time of the second link disruption and its effect. For the runs in experiment 1, the effect of the second link disruption will exist after the transmission starts for 23 minutes, which continue to affect the subsequent data transmission. In comparison, for the runs in experiment 2, there is no data flow existing after the transmission starts for 17 minutes. In other words, the second link disruption event is actually ineffective to the data delivery, and therefore the extra transmission attempts drops by 1. This also explains the declining trend of RTT in experiment 1 and experiment 2 in figure 5, and why the numerical values of the RTT are either 3600 second or 2400 second. Figure 6 illustrates a comparison of the corresponding good put performance between two sets of the experiments. As discussed, good put is defined as a ratio of the data block size and the block delivery time. As we can see, more extra transmission attempts are caused by the link disruption, the longer the block delivery time is. It is found that the link disruption experienced during data delivery leads to extra data transmission attempts, and thus total number of transmission attempts needed for successful block delivery. With an increase of the duration of link disruption, the number of extra data transmission attempts caused by disruption and total number of transmission attempts increase. The RTT and data block delivery time also increase, leading to good put performance degradation. For a given link disruption event, earlier it starts, more likely the number of transmission attempts increases, and thus longer data block delivery time and lower the good put performance are. For a transmission involving more than one link disruption event, their effect to the number of transmission attempts, RTT and block delivery time cannot be linearly added. It is related to the connections among the link disruption events. Although a series of studies have been done for LTP in space networks, how the inevitable link disruption in space affects the performance for reliable data delivery of LTP is missing. There is a lack of solid analytical understanding of the effect of link disruption on LTP, especially in deep space communications. So, in this way, we still need to do more detailed study and do more the research work of this effect as our major future work. Okay, this is my presentation about my paper in this conference. That's all. Thank you. Thank you very much for your listening. And do you have any questions? Thank you very much for listening.